Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to be looking at linear combinations of vectors and the relationship to systems of linear equations. So in this topic, we will review finding linear combinations of vectors equaling a target vector. We will review solving a system of linear equations. We will demonstrate that these are equivalent problems and give some examples. So, up until this point in this course, we have discussed vector operations, and then we discussed the problem of finding a linear combination of vectors that equals a target vector. We've also discussed solving a system of linear equations. Now, these may seem like completely different ideas. However, one of the purposes of mathematics is to find when different problems are essentially the same. Thus, tools that are used to solve one problem can be used to solve problems in the other, and vice versa. This is the core idea behind mathematical abstraction, and we've already seen this in this course, where we have first looked at finite dimensional vectors, considered some of the properties that are relevant, so we define them as axioms, and then we found there were other systems where we could define a scalar multiplication and a vector addition such that it satisfied all those axioms. Thus, the whole idea of mathematical abstraction is do not reinvent the wheel. So, let's recall these two problems. Find a linear combination of n vectors in R to the m that equals a target vector v also in R to the m. The other problem we had was solve the system of m linear equations in n unknowns. Now, what we're going to do is we're going to show that every problem of the first kind can be interpreted as a problem of the second kind, and every problem of the second kind defines a problem of the first kind. Starting with the first problem. Find a linear combination of n vectors in R to the m that equals a target vector v also in R to the m. Well, let's just replace each of those vectors with vectors showing the actual entries. So, the entries of the vector u1 are the entries u sub 1, 1, u sub 1, 2, u sub 1, 3, and because u sub 1 is in R to the m, this goes down to u sub 1 m. The target vector is, of course, the entries v1 through vm. Now, if we multiply each of the corresponding vectors by the scalars, then that just multiplies all the entries in the first vector by alpha 1, all the entries in the second vector by alpha 2, and so on and so forth. But now we just have a sum of n vectors in R to the m, which essentially is just adding each of the m entries of each of the n vectors. So, adding the vectors, we get that the vector on the left must equal the vector on the right. Two vectors are equal if and only if their corresponding entries are equal. So, the first entry of each of the vectors yields this linear equation. The second entry of each of the two vectors yields this linear equation. The third entries, and so on and so forth up until the mth entry, as these vectors are in R to the m. Now, let's compare and contrast that with what we described as a default system of linear equations in n unknowns. Well, in this case, we see that the target vector v sub k is simply the corresponding right-hand coefficients b sub k. The unknowns are alpha sub L in the linear combination question, and in the problem of a system of linear equations, those are the unknowns x sub L. The entries of the vectors give us the corresponding multiples of the unknowns. So u sub lk is equal to the coefficient a sub kl. Now, the reason for flipping the indices is, in the second case, the first index gave us which equation we were in, while the second index gave us which unknown we were multiplying it by. When we converted the vector, linear combination of vectors, into a system of linear equations, the L indicated which vector we were in, and the K indicated which entry of that corresponding vector. So it's just a different notation. So on the left-hand side, we have the lth unknown multiplied by the kth entry of the lth vector. In the right-hand side, we interpret that as the coefficient of the kth equation and the multiplier of the lth unknown. So, yes, the question of finding a linear combination of n vectors equaling a target vector all in R to the m is equivalent to solving a system of m linear equations in n unknowns. Let's go the other way now. Let us start with a system of m linear equations in n unknowns, and let us show that this can be reinterpreted as finding a linear combination of n vectors equaling a target vector in R to the m. So, first of all, we have these m equations. Well, let's create two vectors. The vector on the left will have the left-hand sides of each of these equations. The vector on the right will have the right-hand sides. All right, and this is acceptable because two vectors are equal if and only if the corresponding entries are all equal. Next, if you take a look at the vector on the left, we could split this up into a sum of vectors. So that is what we do here. We have now split the left-hand vector into a sum of n vectors. Now, looking at the first vector, you will notice that each entry of that vector is multiplied by x1. Each entry of the second vector is multiplied by x2. So essentially, this is the first vector multiplied by the scalar x1, and so we can factor that x1 out. We can do that for the rest of the vectors as well. Thus, we have this linear combination of n vectors. Consequently, if we define the vector b to be the right-hand vector and the vector a sub l to be each of those corresponding vectors, L going from 1 to n, then we essentially have the problem of finding a linear combination of the vectors a sub 1 through a sub n, where the scalar multiples are x1 through xn, and the target vector is the vector b. Thus, every question of finding a linear combination of a collection of n vectors equaling a target vector, all in R to the m, defines a question of solving a system of m linear equations in n unknowns. Similarly, every question of solving a system of m linear equations in n unknowns defines a question of finding a linear combination of n vectors equaling a target vector, all in R to the m. Thus, these problems are equivalent, so any mechanism for solving the first also solves the second and vice versa. Alright, so let's convert the following system of 4 linear equations in 2 unknowns into a linear combination of vectors equaling a target vector. Alright, the target vector is just the right-hand sides, and it is, of course, in R to the 4. So it's just the vector 5, 9, negative 4, 0. Now, if we look at the multipliers of x2, in the first equation it's 1, in the second equation it's 0, third equation it's 7, and fourth equation it's 8. So essentially we're multiplying the vector 1, 0, 7, 8 by x2. And the coefficients of x1 are 3, negative 1, 2, negative 6, yielding the following. So here we now see that the target vector is being determined whether or not a linear combination of the first two vectors could possibly ever be equal. Well, in this case, there are no solutions. For example, the second equation tells us that x1 must be negative 9. But if x1 is negative 9, then the first equation tells us that x2 must be 32. Well, negative 9 times 2 plus 32 times 7 is not going to equal negative 4. So there is no solution to the system of linear equations, and there is no linear combination of those two vectors that equals that specific target vector. Now, later on, we may ask, what is the linear combination of those two vectors that comes closest to the target vector? But that is for another day. As another example, convert the following system of 3 linear equations in 3 unknowns into a linear combination of vectors equaling a target vector. Now, this one's a little bit more interesting because the target vector is the 0 vector. The vector that is multiplied by x3 is 7, 8, 9. The vector multiplied by x2 is 4, 5, 6. And the vector multiplied by x1 is 1, 2, 3. Well, not only does this have a solution, it has infinitely many solutions, for there ends up being one free variable. So a solution is this vector here. So x3 is the free variable. Whatever value x3 has, x2 is negative 2 times that value, and x1 takes on the same value as x3. Now, interestingly enough, this solution is simply x3 times a constant vector. Now, if you think back, this is simply all linear combinations, or all scalar multiples, since there's only one vector, of the vector 1, negative 2, 1. Now, that is actually a subspace of R3. We'll look more into that later. Next, let's go the other way. Convert the following question of finding a linear combination of two vectors in R3 equaling a target vector also in R3. Let's convert this into a system of linear equations. Well, because we're in R3, there are going to be 3 equations, and because there are 2 vectors we are taking a linear combination of, we will therefore be having 2 unknowns. So the first equation can be read off the first entries of each of the vectors. Alpha 1 times 1 plus alpha 2 times negative 3 is equal to 8. The next one is alpha 1 times negative 2 plus alpha 2 times 4 equals negative 13. The last is alpha 1 times 5 plus alpha 2 times 7 is equal to 7. Now, this is an overdetermined system of linear equations. That means there are more equations than unknowns. Consequently, it's very likely that no solution exists. However, in this case, there actually is a solution, and that solution is the vector 3.5, negative 1.5. Now, because these scalars are alpha sub 1 and alpha sub 2, we will represent the solution vector as a bold-faced alpha. Convert the following question of finding a linear combination of two vectors in R squared equaling a target vector also in R squared into a system of linear equations. So, once again, reading the first entries of each of the vectors, we have the scalar alpha 1 times 3 plus the scalar alpha 2 times negative 1 equaling 5. So that's 3 alpha 1 minus alpha 2 is equal to 5. Next, reading the second entry of each vector, we get negative 6 times alpha 1 plus 2 times alpha 2 is equal to negative 12. All right. This system, however, has no solution. For if we add 2 times the first equation onto the second, we get that 0 is equal to negative 2, which is never true. Consequently, no solution exists to the system of linear equations. However, we can also see that from the vectors. You'll observe that the vector 3, negative 6 is a scalar multiple of the vector negative 1, 2. Consequently, any linear combinations of two vectors that are scalar multiples of each other is simply going to end up being another scalar multiple of either of those vectors. However, the vector 5, negative 12 is not a scalar multiple of negative 1, 2. So there cannot be any solution to the first question either. Now, if the second entry of the target vector was -10, then yes, there would be a solution, and in fact, there would be infinitely many solutions. Following this topic, you now understand that the two presented problems are equivalent. Finding a linear combination of n vectors in R to the m equaling a target vector, and solving a system of m linear equations in n unknowns. You know that we will now be looking forward to solving tools for the first, and once we use those tools and find them, we can also use those tools for solving the second. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!